This is an ATtiny 412 microcontroller controlling 12 LEDs using only 4 pins. The LEDs are being turned on and off randomly, which makes a pattern that is pleasing to the eye. How does this work? It's done using a well-known technique called Charlieplexing. Among other things, it allows n pins on a microcontroller to control n times n-1 LEDs, so 4 pins can control 4 times 3 or 12 LEDs. There are many sources of information on Charlieplexing, but I made this video to show it in action on an ATtiny 412 and to give what I hope is a crisp but complete explanation putting everything I think is needed into one place. So, how does this work? Let's use n equal 3 pins for diagrams. Start by imagining n pins on a microcontroller each connected to a current limiting resistor. Also imagine n squared identical LEDs arranged in a square. Now, delete all of the LEDs on this diagonal. Charlieplexing cannot handle them. This leaves us with n times n-1 LEDs. There were n LEDs on the diagonal. This leaves us with the number of LEDs that Charlieplexing can handle. Connect the cathodes in each column of LEDs to a pin. Connect before the resistors. Next, connect the anodes in each row of LEDs to a pin. Connect after the resistors so the resistors limit the current flowing into the LEDs. We'll talk below about the value of the resistors. It's a tricky topic. You don't have to connect the anodes in a consistent row order. Just connect all of the LEDs that share a cathode signal to different anode signals. It's also okay if you have fewer LEDs. You don't have to connect all anodes to all cathodes via an LED. Finally, we light an LED. If we set PA7 to be an output driving high, PA2 to be an output pulling low, and PA6 as an input, then the LED shown lights. This works because an output pin driving high is like a connection to VDD via a transistor inside the microcontroller. An output pin pulling low is like a connection to ground via a different transistor inside the microcontroller. Thus, we have the current flow shown, and the LED lights up. Here's a schematic of the heart of a pin's output stage. It shows how the transistors make these connections. You can pause and study this if the concept is unclear. This is how pairs of output pins can make a circuit. A pin configured to be an input has a very high impedance, think resistance, so it acts like it is not connected to anything. You can light any single LED this way. Set its anode pin to a high output and its cathode pin to a low output, and then set all other pins to be inputs. In fact, we could light any subset of LEDs in a row by making multiple pins into low outputs. But there is a problem. We are using one current limiting resistor from one current source for multiple LEDs. The current gets divided among the LEDs, and they shine less brightly, making the LED brightness variable depending on the number of LEDs lit. That's bad. It's not harmful, but it's bad, so avoid doing it. We can also light any subset of the LEDs in a column by making multiple pins into high outputs. PA2 is syncing the sum of the currents sourced by PA7 and PA6. In general, the sink sinks n-1 times as much current as the individual source's source. We must choose resistor values such that the datasheet's sink current limit is respected. For large N, this can appreciably dim the LEDs, but there is still more to this story. Rows and columns contain n-1 LEDs. With larger n, more than n-1 LEDs can be lit at the same time. Here's an example for n equal 4. But there are problems, such as current dividing. With the resistor placement I'm using, working by column is a good plan. It means n-1 LEDs in the same column can all be lit at the same time. Of course, the LEDs don't need to be placed in squares on the board. The square just explains the electrical connectivity. But how to light any subset of all of the LEDs? We have to work in a cyclic fashion, lighting the LEDs in one column and then the next, and so on. This must be done quickly so the eye does not perceive the LEDs blinking, at least 50 times per second, but a bit faster is better. This also reduces the apparent brightness of the LEDs because their on-duty cycle will be at best 1 over n. For n equal 4, any LED that is supposed to be on is actually lit only 1/4 of the time. With just one LED lit, the oscilloscope shows that the LED is actually blinking at just under 130 Hz. The duty cycle is 25% because we are using 4 pins. can we compensate by reducing the value of the resistors on the theory that peak current for sourcing and sinking can be higher than what the datasheet allows for constant currents? Probably yes, but datasheets may not give complete information on peak current limits. Read the datasheets and then be conservative in proportion to how little guidance the datasheets provide. At least modern LEDs are quite bright. We have that going for us. If you Charlieplex different types of LEDs rather than using identical LEDs, you may need to use a resistor for each LED and choose different resistor values to balance the brightnesses. These factors and the software complexity of the column cycling suggest that Charlieplexing may not be the best idea for large N. Alternatives include I/O expanders to give you more pins, and ICs that are designed to drive lots of LEDs. With this quick explanation of Charlieplexing out of the way, let's take a quick look at the ATtiny 412 software. It will be available on GitHub, link below. Here's the software in the Arduino IDE, and we start by defining the 4 pins that we're going to use, and we do that by giving their bit position within the port A registers, and that's because we're going to write directly to those registers. Next, we'll skip down to this array of pins, and I need that because we work cathode by cathode. So essentially an index to this array will indicate the current cathode. And now, volatile global variable val to display is used to communicate to the interrupt service routine that actually sets the LEDs. So the main loop can set val to display to determine what gets shown on the LEDs, and we'll scroll down to the main loop and look at that. So here it is. And what that's doing is just every 150 milliseconds, it writes a random number to val to display, and that makes the LEDs show a random pattern. And while we're down here, let's look at setup. What that's doing is configuring the periodic interval timer to be the timer that determines when the LEDs change state. And so it's being set to generate an interrupt every 2 milliseconds. And so the interrupt handler for this interrupt is the thing that does the LEDs. So now let's scroll up, and we come to this data structure here, which we need to look at. This two-dimensional array bit table needs a diagram. Val to display contains a bit for each LED. First, bit table associates each LED with its cathode pin. All LEDs in a row share the same cathode pin. Second, each bit table entry contains a bit position in val to display and the anode pin. The interrupt service routine sets the pin for the current cathode to be a low output. Then it loops over the cathode's row in bit table and, for every entry, sets the anode pin to a high output if the corresponding bit in val to display is a 1. That's how the LEDs get lit using the cycling through cathodes scheme. We'll scroll down to the actual interrupt handler, and it's right here, and the first thing that it does is clear the interrupt. And I made a video about the periodic interval timer previously. I'll try to remember to put a link below. After that, it sets all of the pins to be inputs, and that's just to make sure there are no conflicts, and it sets the previous cathode to be an input, which I need to do anyway. And then down here is the loop that goes through the row in the table, the row in bit table for the current cathode, and it collects the values of anodes that have to be enabled as output highs. Then it sets the cathode pin to be an output low, the current cathode, and here's where it sets the anodes. And those two writes right there. And then after that, in preparation for the next time the interrupt service routine gets called, it sets the cathode to be the next cathode in the cyclic pattern. So this is how the software works. That's Charlieplexing in a nutshell. I'll end this video here. See below for links, and thanks for watching.